Today I have the privilege to hold in my hands something very special. This is the world's first operational gear-based continuously variable transmission, or CVT. And before I explain how this piece of absolute mechanical poetry actually works, allow me to first explain why a gear-based CVT is a big deal. As we said, CVT stands for continuously variable transmission, which means that it's continuously varying something. And what it's varying is its gear ratio. I'm saying it with air quotes because traditional CVTs, they don't really have any gears, but they can still assume any gear ratio at any one time. And this makes them the ultimate transmission from the perspective of ease of use, smoothness, and fuel efficiency. And while I would not choose a CVT for something that I want to take to the track or to a twisty mountain road where I want to have fun and enjoy shifting and revving out the engine, I would definitely choose a CVT for something that I'm going to drive every day, especially on the highway or in boring stop-and-go commuter traffic. And it doesn't matter if that something is a car or a bicycle or a scooter, I would choose a CVT for any commuter vehicle because with a CVT, it's impossible to be in the wrong gear. A traditional manual or automatic transmission has a set number of gear ratios or speeds, something like this. A gear ratio of 3.6 or 3.6 to 1 tells us that for every 3.6 revolutions of the engine, the wheels only make one revolution, while the torque at the wheels is increased 3.6 times. So the first gear reduces vehicle speed but increases torque. This is why it's used for getting the vehicle moving from a standstill and for climbing steep hills. On the other hand, a gear ratio of 0.7 tells us that for every 0.7 rotations of the engine, the wheels make one rotation, while their torque is reduced 0.7 times. So this ratio reduces torque while increasing speed, which means that it's great for high-speed cruising on the highway where the vehicle already has massive momentum and just wants to maintain that high speed. The other gear ratios in between these two cover the endless number of other scenarios between starting and high-speed cruising. Compared to this, a CVT looks something like this. As you can see, we only have two quote-unquote gear ratios or speeds. This is because a CVT does not have gears. Instead, we have two conical pulleys and a belt or chain running around them. We slide the belt along these pulleys, and the different sizes of the pulleys at different parts of the cone simulate an endless number of different gear sizes, which means that a CVT has an endless number of ratios in this range between its lowest and highest ratio. So if an automatic or manual is a 6-speed or a 5-speed or 7-speed or whatever, then a CVT is a million-speed transmission or an infinite number of speeds transmission. This is a great thing for fuel efficiency and smoothness and even acceleration because an engine is not equally efficient and not equally powerful at all RPM. A typical engine is going to have peak efficiency at something like 2,500 RPM and peak power at, let's say, 6,000 RPM. These can, of course, vary a bit, but usually it's something like this for your average modern engine. Now, let's imagine a scenario where we transition or accelerate from 60 km per hour to 100 km per hour with a manual transmission. As you can see, we will cover one half of our speed range with one gear and the other half of the speed range with a different gear. Both of these gears allow peak efficiency or peak power for only a short moment within the speed range. Outside of these two moments, our gear ratios are just a compromise. On the other hand, what a CVT will do in the same scenario is that it will constantly vary the gear ratio to either keep the engine at peak power or at peak efficiency RPM, depending on the wishes expressed by the driver through the throttle pedal. This leads to a somewhat unfamiliar driving sensation for those used to traditional manuals or automatics, and that's because once the engine reaches the target RPM, it will constantly stay at that RPM while vehicle speed will be changing. Well, yes, the driving sensation is a bit weird at first, but the benefits are undeniable. Not only are there no noticeable shift points and vehicle jerking, but we're also saving fuel or gaining acceleration by keeping the engine at the target RPM all the time. In other words, a CVT does work for the engine, instead of the engine having to do work for the transmission by revving through every gear and spending more time outside the target RPM. Okay, that's great. So CVTs are amazing. If they're so amazing, why aren't they on every car, truck, motorcycle, and bicycle? Well, they're not because traditional CVTs, they kinda suck. They suck because, yes, they do improve the fuel efficiency of the engine, but they themselves are not very efficient. And that's because friction lies at the core of the design of a traditional CVT. If you observe the inner workings of a CVT, you will see that the belt or chain has nothing to grip onto. There are no teeth, no notches, no grabbing points, nothing, no shapes. And that means that the belt tension, or the friction between the belt itself and the smooth surface of the pulley cone, are the only thing transferring the torque. Which means that to transfer substantial amounts of torque, we need substantial friction. And as we know, friction leads to efficiency losses, heat, and wear. This is why a typical belt or chain CVT in a car is around 80 to 88% efficient. A more simple scooter CVT is around 70 to 75% efficient, whereas a geared manual transmission is 95 to 97% efficient in almost all applications. But efficiency is just the beginning of our problems with a CVT. Because we have high friction, it also means that we have high heat, which means that a CVT needs a lot more cooling compared to a traditional manual or automatic transmission. We're also torque limited with a CVT because we rely on belt or chain tension to transfer torque. Too much torque, and the chain is quickly going to start slipping, leading to very much increased wear and tear on a CVT. This is why you'll be hard-pressed to find a CVT on a mass-produced high torque and high performance application. But with a geared transmission, we really don't have any of these problems. We have gears or shapes interlocking. We don't need friction because we have one tooth pushing on the other tooth. We have mechanical leverage for transferring torque, which means greatly reduced friction and improved efficiency. Also, we're not really torque limited because we have mechanical shapes interlocking. So if we want the ability to transfer more torque, we're just going to make the gears wider or make them from a stronger material. All of this is why researchers and scientists and inventors have for a very long time been trying to combine the benefits of a CVT with the benefits of a geared transmission. The ease of use, the smoothness, and the continuously variable gear ratio of a CVT with the high torque capacity and reduced friction and improved efficiency of a gear-based transmission. Unfortunately, there has been very little success until 2016, when a man named Edison had a breakthrough idea. He decided to split the rotation. Now, this may sound confusing, but bear with me, it's going to make a lot of sense really soon. Now, what we're going to do is that we're first going to explain this transmission, which is one of the earliest practical adaptations of this split rotation approach. And when we understand this one, it's going to be a lot more easier to understand this one, which is a more advanced, more capable, more recent prototype, but it works on the absolutely same operating principle of split rotation. Now, if you look inside of this transmission, which has a convenient peaking window, you may notice that some of the gears appear stationary some of the time. It's actually a lot easier to do this with CAD. Now, I want you to think of these three small gears as runners in a relay race passing a baton to each other. When a gear is marked with a red dot, that particular gear is at that time doing the job of transferring and manipulating the torque from the transmission input to the transmission output. You can observe how this task is passed from one gear to the other while the transmission is operating, just like a baton in a relay race. Now, to understand what is actually happening, we must observe a single small gear and its arm together with the planet gear that the arm is attached to. Now, the arm is attached to the planet gear via a freewheel, which means that the gear can rotate independently of the arm. But this only happens when the center of the arm axis, or point of rotation, coincides perfectly with the axis of the planet gear. The transmission also includes a mechanism which can offset or move the axle of the arm. Now observe what happens when we offset the axle of the arm from the axle of the large planet gear behind the arm. The arm no longer remains stationary in the center of the gear. Now rotation of the large planet gear causes the arm to move. In other words, we have just created leverage. If we put our small planet gear into a ring gear while the arm axis is offset, we will apply this leverage onto that ring gear. What will happen is that the small planet gear will essentially drag the ring gear. Of course, this only happens during the point when the leverage created by the axis offset of the arm is in a favorable position in relation to the ring gear rotation. As the arm continues to move, the leverage created by the axis offset disappears in relation to the ring gear, and the small planet gear simply freewheels along the ring gear. But as one leverage disappears, another axis offset leverage appears, and so the torque transmission is simply relayed to the other gear, and so on and on. As you can see, we are splitting the rotation, and each small planet gear handles the torque transfer over a portion of the rotation. We manipulate the torque and the speed of the transmission by manipulating the axis offset of the arms. It's important to understand that our leverage begins here, at the teeth of the large planet gear. This is the point of contact that rotates the gear. Our leverage ends at the sliding pin, the moving point that gets the offset. As you can see, at minimal offset or low gear ratios, we will have maximum leverage, which results in maximum torque. But we also have minimal speed because the circle drawn by the pin is very small during small offsets. And remember, each planet gear is active during only a portion of this small circle. This means that the small planet gear drags the ring gear by only a minimal distance, resulting in low speeds. Now observe what happens as we increase the axis offset. Our leverage decreases, but the circle drawn by the sliding pin increases. So our torque decreases, but our speed increases. The small planet gear is still active for the same period of time, but because of the greater circle of the sliding pin, it drags the output gear a greater distance during the same time, resulting in greater speed. Now observe something interesting that happens when each of the arms have zero axis offset. In that scenario, all three arms just sit still and everything pretty much just freewheels. We have input speed and torque, but zero output speed and torque. This is where the name ratio 0 comes from. The transmission can also have a ratio of 0, unlike a traditional CVT. And this means that there is potential to eliminate the clutch from the vehicle, depending on application and vehicle type. And I don't mean the clutch pedal, I mean any kind of system that needs to connect and disconnect the engine from the transmission. And finally, here you can see the early prototype operated on a bicycle. Now, this is a more recent, more advanced, more capable prototype designed to overcome some of the shortcomings of the early design. Although the new thing may look radically different compared to the old one, it still operates on the absolutely same principle of split rotation as the design we just explained. Let's observe. Okay, here's our input. And here's our output. Now observe what happens when I rotate the input. As you can see, I had to make around 2.8 rotations of the input to achieve a single rotation of the output. That gives us a gear ratio of 2.8 to 1. Now, this transmission is also intended for a bicycle, and as you can see here, we have a little joystick control that we attach to the handlebar. This joystick operates a tiny little 10-watt motor that we use to change the gear ratio. Of course, it's easy to imagine how we don't have to do this manually with a joystick. The gear ratio can be changed 100% automatically using electronics and sensors. Now observe what happens when I press on the joystick. This element here converts horizontal sliding into arm axis offset. As you can see, now that we have changed our arm offset, we need to complete approximately only 1.2 rotations of the input for 1 rotation of the output, giving us a gear ratio of 1.2 to 1. Of course, an infinite number of gear ratios between these two is possible, and the transmission is also in a sort of limited safe test mode right now, and it can actually have higher and lower gear ratios than the two extremes I just showed you. Okay, now let's see how it works. Here we have our arms, which are again attached to freewheels, which are on the shaft of a gear that meshes with the output gear. We have 4 such arms, which all jointly relay the torque transfer amongst themselves to generate the final torque and speed value at the output gear. So again, we change the arm offset, which changes the leverage each arm produces on the output shaft. Observe how in this moment the arm offset applies leverage on the output gear shaft. As we continue to rotate, the leverage disappears. But now this other arm is in the ideal position to apply leverage. When this leverage disappears, another arm takes over, and so on and on. Again, as you can see, the rotation of the output is split, and the baton of torque transfer is passed from one arm to the other, just like in the initial design we explained earlier. But here's something else that's very interesting on this prototype. If you observe carefully, you will notice how this gear and this gear too are not perfectly round. Instead, they are elliptical. You may be familiar with elliptical gears from large industrial printers or other applications where they're used to vary the rotation speed. Well, here they do the opposite. They equalize the speed. If we go back to our CAD animation of the initial design and you observe the leverage created by the axis offset in relation to the small planet gear, you can see how the position or the orientation of the leverage changes. This is just like the position of the crankshaft stroke in relation to the piston in an engine. The same thing happens in our transmission, of course, and variable leverage means that we have a variation in the acceleration of the small planet gear that drives the output ring gear. The greatest variance in the leverage actually occurs when one gear transfers the baton to the other, and the final result is a slightly oscillating speed output from the transmission. Now, this is barely noticeable or even completely unnoticeable in some applications, and it isn't an issue for an eventual engine that might be connected to a transmission like this, but a homokinetic or equal non-oscillating speed and torque output is generally preferred. So the two elliptical gears are used to slow down the output when the offsetting pin tries to accelerate it, and vice versa, leading to an elimination of speed oscillation. Now, you might be wondering what this sound is that you can hear when I rotate the transmission. This is actually a one-way ratcheting mechanism inside of these parts, and what it does is that it prevents the output shaft from acting on the input. As you can see, when I turn the output, nothing is happening on the input shaft, and that's because this transmission is intended for a bicycle. And imagine a scenario, we're going downhill with a bicycle. We want, of course, to prevent the increased output shaft speed from forcing our legs to pedal faster. Instead, we want to keep our legs stationary and we want the pedals to freewheel, and that's what the one-way ratcheting mechanism achieves. Now, the company has developed another design on the same working principle, but this one is much less compact, but much more robust, which means it's intended for cars, trucks, and other high torque applications. So, a gear-based CVT, something that sounds impossible, but was made possible with mechanical ingenuity and creativity. I have to be honest, it's been a pretty long time since something from the world of mechanical engineering blew my mind the way this transmission and its split rotation approach did. So, this is a product in pretty late stages of development, but it's still not a commercially available product. There's a lot of research and development and experience behind it, but it must still go through one more phase before you can buy it or find it in OEM vehicles in the world around you. That final stage is a lot of laboratory testing, a lot of wear, strength, reliability tests, streamlining the product for mass production, noise, vibration, harshness, so on and on and on. This is a very, very time-consuming and very expensive stage of product development, which means that Ratiozero is currently looking for partners to help them get through this stage. And if you're interested in becoming a partner, then you can do so by getting in touch with Ratiozero through their website, which I have linked in the description of the video and the pinned comment. Something else very interesting from them is that in the near future, we will have the first practical pairing of this technology with an internal combustion engine, because Ratiozero aims to develop and test their transmission on a Yamaha T-Max scooter. And so that's pretty much it. Before I end the video, I would like to say a very big thank you to Ratiozero for giving me this amazing opportunity to do an exclusive demonstration of this very interesting technology on my channel. And as always, thanks a lot for watching, and I'll be seeing you soon with more fun and useful stuff on the D4A.